Good morning, my dear students. Again, so in this PPT, I'm going to explain you about the new topic, that is rotating and reciprocating unbalance. Okay, so this is a continuation of that. What the definition related to forced vibration. Okay, what we studied in the last class. Okay, so here I told you number of times forced vibration is nothing but what the system vibration takes place due to the external forces, that is the external agent of a periodic forces is called as forced vibration. Okay, whereas in the free vibration we are not going to apply any external force, the vibration occur itself is called as free vibration. Okay, so in normally the any mechanical system, even you can take the compressor, rotor, engine, vehicles. Okay, there is a lot of the rotating parts in where the component having the rotating parts, there is a lot of unbalance takes place. Okay, that we need to study in this equations. Okay, in this topic. Okay, with the help of some equations. Okay, so here the rotating or reciprocating unbalance, two topics, and this topic is also most important for the point of examination. Okay, so they may ask you write a note on rotating unbalance and reciprocating unbalance. Okay, so and as compared to both, the rotating unbalance is very important. Already we studied about in the module 2 just the concept of the what is the rotating balancing and reciprocating balancing. Okay, so normally generally the rotating and reciprocating of any machine component produces an unbalanced force due to the inertia forces of the moving parts. Okay, so even if you take any rotating parts, turbine, blade, whatever, if that is the unbalanced takes place, it is because of the inertia forces. Okay, if the wear and tear of the takes place of any mechanical component, there is a chance of there's a chance of not considering the axis of the shaft. Okay, if the center of the gravity of the any mechanical component does not coincide with an axis of the shaft, that is axis of the machine component, then there is a chance of creating a unbalance. Okay, so in a rotary system, that is in a rotating part, the in any rotating system or any component having a one or more rotating masses, if the center of the masses of the system does not lie on the axis of the rotation of the shaft, that is the rotation of the system is called as unbalanced. This sentence is very important, I have to write in the examination. Okay, if the center of the masses of the system does not lie on the axis of the rotation, okay, and the axis of the rotation of any system is there is a chance of creating an unbalance. Okay, so even that is that may be any component. Okay, so here the rotating unbalance, normally it is the uneven distribution of the mass around the axis of the rotation. Okay, what do you mean by rotating unbalance? So it is uneven distribution of the masses around the axis of the rotation of the machine component. Okay, so a rotating mass or a rotor is said to be out of the balance when its center of the masses, that is the inertia masses, is out of the alignment within the center of the rotation, that is the geometrical axis, then we are going to call as rotating masses. Okay, so unbalance causes a moment which gives the rotary of a wobbling moment characteristics of a vibration of a rotating structure is called as unbalance. Okay, it is because of the it causes the unbalance. Okay, how we are going to having some equation, that is a derivation for this equation. Okay, rotating unbalance, because we have to solve the numerical problems on this. So I hope you understand this rotating unbalance. Okay, so if any system that the center of the gravity does not lie on the axis of the then geometrical axis, then there is a chance of creating an unbalance, that is called as rotating unbalance. So now we are going to consider one mechanical system. Let us understand deep. Okay, so this is about the equilibrium position, and this is figure B shows the equilibrium position, and figure B shows what the figure A shows the equilibrium position, and figure B shows the displacement, that is the displaced position. Okay, consider a mechanical system, any component. Okay, it is the total mass. Okay, the total okay, this is the total plus, this is the equilibrium position, that is the axis. Okay, so this mechanical system, having to reduce the vibration, we are going to use this isolation, that is the spring stiffness and the damper. Okay, so here from point 0 to m is an eccentricity, that is a distance. Okay, so here a small mass will be fixed. Okay, this is about the m naught. Okay, m naught is nothing but the unbalanced masses. Okay, so here the cg will be there, this is the vertical axis, this is the horizontal axis. Okay, just to give the displacement x. So here the figure B shows the displaced position. Okay, just to display this diagram. So here if you displace this, the center of that original point, the O will be displaced at a distance of x, I shown here. Okay, that is from mean equilibrium position to some distance. Okay, that distance is x, that is the center of the gravity, that is the O. Okay, so here when the component is rotating in this, when the shaft is rotating, there is a chance of producing a angular that is what, a centrifugal force. Okay, so centrifugal force in this direction, what we are going to get, m naught e omega square. Okay, along with this we have the one more horizontal forces and vertical component. Okay, so this is about the figure B shows the displacement diagram and component. Okay, So let to m is the total mass of the machine. Here the capital M is the total mass of the machine including the unbalanced mass. That is, this is the total mass, this is the m naught is unbalanced mass. Okay, so m naught is unbalanced mass in kg and E is equal to eccentricity of the unbalanced mass. Whereas in the centrifugal force, what we are going to consider here, where we are going to consider the R, radius of rotation. Okay, here we are going to take the E. Okay, so that is about the centrifugal force. Okay, so here the same I wrote here, and this component while rotating, there is a forces acting on this. So let us draw on the free body diagram of this. Okay, so what all are the forces acting on that element we are going to consider here. Okay, so here the motion takes place in a vertical direction, horizontal we are going to rigid. Okay, when a component is rotating, there is a centrifugal force m naught, that is unbalanced mass m naught E omega square, and the horizontal component, that is m naught E m omega square cos omega t. We are going to consider horizontal component as cos and vertical is sin. Okay, there are three forces are acting. So okay, this is called, and the downward spring force, this is the damper force kx and ky. Okay, so now according to the D'Alembert principle, we are going to solve this equation. So D'Alembert principle state that what summation of inertia forces plus external forces is equal to 0. Okay, so upward direction forces you are going to consider positive, and downward direction consider positive value going to consider as negative. Okay, so here the upward is so here this is the upward direction, it is in terms of the sign. So that m naught E omega square sin omega t minus mx double dot, this is the inertia forces acting downward, minus kx minus cx. Okay, so now again this equation is just to modify this equation, that is negative sign values transferred into RHS, that is mx double dot plus cx dot plus kx is equal to m naught E omega square sin omega t. So this is give equation number 1. Just to rearrange this equation. Okay, so we are going to get what, this equation number 1. Okay, but we know that the force vibration to the due to the external excitation harmonic wave equation. Okay, so that equation was what we know that. So this is the external force, that is a harmonic force equation is f naught sin omega t. Okay, just we know that this. Okay, so give equation number 2, I think this. Okay, so here give equation number 2. Okay, so now compare equation number 1 and 2. So f naught value, what we are going to get, m naught, that is unbalanced mass E omega square. Okay, so this is the f naught value, give equation number 3. Okay, now we know that the steady state amplitude of the force, that is a force vibration is given, but what, so x is equal to f naught divided by k whole divided by square root of 1 minus omega by omega n whole square whole to the power whole square minus 2 zeta omega by omega n whole square. Okay, so this is the equation we already derived in the previous slide. Okay, so previous ppt. Okay, so now x is equal to what here, we know that the f naught by k. Okay, k is equal to what, here we derived omega n square root of k by m, omega n square is equal to k by m, k is equal to what, m omega n whole square. Okay, so that is square, wherever k is there, just to substitute m omega n square in this equation. So m naught E omega square by k, so whole divided by, you are going to get denominator as it is. Okay, so take the numerator, so m omega square E divided by whole square is equal to what, m naught E omega square whole divided by k is equal to what, you just to replace this m into omega n square. Okay, so this is equal to what, m naught, just again you this again you have to simplify this. Okay, so this m naught k this what, m naught E, so omega square whole divided by mass m omega square omega divided by omega whole square. Okay, just this will be cancelled. Okay, so here what you are going to get, but in place of k is equal to, just to substitute, you are going to get this equation. Okay, so therefore the x is equal to, again this value substitute in the top equation, that is okay, x is equal to m naught, that is unbalanced mass eccentricity divided by m omega by omega n whole square whole divided by square root of 1 minus omega by omega n whole square to the whole square minus 2 zeta omega by omega n whole square. Okay, so this is the equation for what, the unbalanced that is a rotating unbalance. Okay, so that again just to modify this, so you are going to get this final equation. Okay, so this equation is called as what, the steady state amplitude for unbalanced rotating mass. Okay, so this x is called as what, you have to remember capital X is equal to steady state amplitude for the unbalanced rotating mass m naught. Okay, so while solving the problem, you are going to get this equation. Okay, so same I wrote here. So again the phase angle is equal to what, so tan inverse of 2 zeta omega by omega n divided by 1 minus omega by omega n whole square. Okay, this is about the phase angle. These two equations you have to remember. Okay, in the while solving the problem. Okay, how I will write this equation direct while solving the problem, you have to remember. Okay, so m naught, that is unbalanced, eccentricity total mass, it is omega by omega n, this remaining is as it is. Okay, so again the second part is the reciprocating unbalance. Okay, so we know that the reciprocating unbalance, again it is similar to that only. So it is also takes place due to the displacement position of the axis. Okay, so that is called as reciprocating unbalance. Okay, So here this equation is different. Okay, so let m be the equivalent mass of the reciprocate. Let us assume the m is the equivalent mass, that is the total mass. Equivalent mass means the mass which is fixed in the component. Okay, m is the total mass of the included mass. Okay, l is the length of the connecting rod, r or e is the length of the crank. So inertia force due to the reciprocating parts, we are going to get this equation. So since e is very small, so neglect that, that is in a second harmonic force. So therefore the exerting force on that particular system is equal to m omega square e sin omega t. So again in another way we are going to solve that. Okay, so let us consider this is an equation that is a mechanical system. Okay, so this system is attached to a stiffness and a spring damper which is attached to the ground lever. Okay, so here the axis axis, this is about the original center. Okay, just if you give some, this is called as the referential axis. Okay, reference axis. Okay, and this can be rotation with an angular velocity. So if you rotate this, we are going to get the horizontal component one force. And okay, so here from original position to here the crank, this is a connecting rod. Okay, from m naught to e, connecting rod denoted by l, and with an angular circular frequency omega. So here the omega into t, this is the angle, and the total angle is theta. This is the total mass m. Okay, so again same, f1 is equal to m naught r omega square, that is the angular frequency, that is a what, that's a centrifugal frequency. So cos theta plus sin theta we are going to get here, cos theta. So here the two along the horizontal component, we are going to consider the cos, and vertical you are going to consider the cos 2 theta. Okay, cos theta plus cos 2 theta divided by n. Okay, again cos theta, how you are going to just to modify this equation I shown here. Cos theta can be written as sin 90 minus theta. So same you write here sin this as it is m naught r omega square sin omega t plus sin 2 omega t n by so sin 2 omega t divided by n. Okay, so where n is called as the oblique ratio, that is given by l by r. Therefore the for high speed engine, so normally high speed engine we are going to get the force equation f naught is equal to m naught r omega square sin omega t. So this is the equation for for the reciprocating unbalance. This equation we are going to use while solving the problem. Okay, so you have to remember these two equation. One is so either you can use this exerting force is equal to m omega square e sin omega t. Okay, or that. Okay, both are same only. Okay, so m naught r omega square sin of omega t, both are same equation. So this equation is for the reciprocating unbalance. The previous case one is what, rotating unbalance. Okay, both the equations very important while solving the problems. Okay, you remember this. Okay, I hope you understand this. Thank you.